So, we were talking about curvature, and what I wanted to do now is to complete the story by telling you something about geodesic deviation. And I'm going to spend a little bit of time on that because, well, first of all, I think probably you've seen this before again. We're doing review stuff. But I don't think you've seen the derivation I'm going to give you of the equation of geodesic deviation before. And I think there's something pretty about this derivation and something also that's going to be useful as build-up for what we're going to be doing next, probably starting next week when we start talking about congruences of geodesics. So I want to introduce basically a way of approaching certain derivations that I find compelling, and I find it's a very nice way to do things. And I'll use that in the context of deriving the equation for geodesic deviation. So, that's the topic, and it's really, I think, the thing that characterizes in the most immediate way what curvature does when you're dealing with curves in or geodesics in a curved manifold. Well, just to do a couple of very simple examples. So if we take the surface of the Earth or the surface of a sphere, more generally speaking, and we take geodesics that are propagating on that surface, so we know that geodesics of a sphere are going to be the great circles of that sphere. And I can imagine taking one of those geodesics, starting it off at the equator somewhere here, and following a great circle. I know that I will end up from the equator at the North Pole. So that would be the great circle that passes through the equator at 90 degrees and then joins up at the North Pole. So that's an example of a geodesic, and another example of a geodesic is another one that starts at the equator, but from a different spot, and also ends up going all the way to the North Pole. So both geodesics are starting at 90 degrees from the equator, and they both merge at the equator. So this property that geodesics that are starting parallel, converging to a point or getting closer together, more generally speaking, is something that directly has to do with curvature. In flat space, of course, it would never happen. Geodesics that are parallel, well, in flat space, geodesics would be straight curves, and straight curves that start parallel will always be parallel. The fact that here we start parallel and we end up converging to a single point, or more generally speaking, the fact that we start parallel and end up, the geodesics approaching each other, is a property of curvature. It's also that gives us the gravitational meaning of what the curvature tensor is doing. It's really this property that geodesics end up converging toward each other or diverging away from one another that tells us something about the curvature. So the context for gravity would be something a little bit different, where, for example, here we have Earth, and here we have, somebody freely falling toward Earth in this particular direction, and somebody else over here free falling toward Earth along this particular direction. We have two freely falling observers in a gravitational field. Each observer is following a geodesic, so each observer, as far as they're concerned, are moving in a straight line in a space-time. Each observer, as far as they're concerned, being freely moving, have no immediate way of detecting gravity. So all local experiments that they might do, playing with balls, juggling with balls, and all of this, in each of the local frame of each observer, would reveal no sign of gravity in their immediate vicinity. So they're each falling down, but you'll notice that the trajectories are getting closer together. So the geodesics are converging together, and even though here I was not talking about geodesics starting parallel, nevertheless we have geodesics converging together because of the fact that the gravitational field is not everywhere constant. It varies in direction. It goes toward the center of the Earth, and it's this inhomogeneity in the gravitational field that is probably the most important aspect of a true gravitational field. And it's that property that's associated with curvature. So you know, in general relativity, when we start from the metric, we're really starting in Newtonian terms with the potential that gives rise through a gradient to a gravitational force. So the metric is the potential, the gradient of the metric is the Christoffel symbols, that is analogous to the gravitational force. The gradient of the force is the feature that the gravitational field is inhomogeneous, that the field is pointing in one direction at this position and in a different position, in a different direction at that position. It's the inhomogeneity in the gravitational field, or the gradient of the force, that tells us something meaningful about gravity. It tells us something that, and you know, it's that property that's associated with curvature. So metric is potential, gradient of metric is the force, and gradient of the force is the Riemann tensor. It's the curvature. It's the thing that really tells us something meaningful about gravity. A constant gravitational field, a field that would be constant in magnitude and direction everywhere, is not a real gravitational field as far as GR is concerned. It's something that would be completely equivalent to boosting yourself in an accelerated frame. It's completely, equivalent to a quarter transformation, and that would be a field that has no curvature. And a field that has no curvature is no real field at all. So to have a real gravitational field in GR, you have to have curvature. And the manifestation of curvature in an experiment like this is this property that freely falling observers will either converge or diverge either converge or diverge. Geodesics will tend to approach each other, or repel each other, or diverge away from one another as a result of curvature. So there's a parallel between something that is purely geometrical and something here that's purely that's gravitational. I mean, in both cases, we have this behavior of geodesics getting closer together here or here, and that basically is the physical connection that we're making between something purely geometrical like curvature and something purely physical. And all along, I've been talking about the tidal aspects of gravity. So the gradient of the gravitational field, the gradient of the gravitational force, is what we call the tidal forces, and that's something that's directly associated with curvature. All of that then, all that I've talked about, either this effect over here or this effect down here, is something that's contained in the equation of geodesic deviation. It's the way that that reveals most clearly, I think, the physical meaning or geometrical meaning of the curvature tensor. Okay, so I wanted to talk about this, and we will, and I wanted also to talk about this and use that as an excuse to introduce a geometrical way of approaching problems like this, where we're trying to say something about the behavior of neighboring geodesics. And that's something that I'm going to do now for the first time, and then later on we'll do it again in the context of congruences, probably starting next week. So what we want to do is to describe the behavior of one geodesic relative to another reference geodesic. So here's my reference geodesic. I'll call it gamma 0. And that's a geodesic in space-time. And I'm going to introduce another geodesic that I may imagine is starting parallel, or more generally speaking, is just starting in a different direction at a different position. But both curves, gamma 0 and gamma 1, are geodesics. What I want to do is to describe the behavior of gamma 1 as seen from gamma 0. And what I want to introduce is a notion of a deviation vector that takes me from gamma 0 to gamma 1. If we were doing all of this in flat space, there would be no problem. We would just draw a vector from a point here to a point there, and that would be our deviation vector. But we know that in a curved space-time, we can't possibly do that. There's no notion of a vector in space-time that points from one point to another point. That just doesn't exist. So in order to introduce this notion of a deviation vector, we have to work a little bit more. We have to introduce a few more things in that drawing in order to be able to do this properly. So, so part of the setup here is to just introduce precisely and meaningfully what we mean by a deviation vector between two curves. And the key to do that is not to stop at two curves, but say that if I can draw a curve gamma 0 and gamma 1, presumably I can draw a whole bunch of curves in between. So instead of talking about two curves, I'm going to introduce a sequence of curves that span from gamma naught to gamma 1. And that's an example of what we'll mean later on by congruence of geodesics. So we have gamma 1, gamma naught, and gamma 1, but in between, I'm just going to draw a whole bunch of interpolating geodesics that I can think of, as a continuous transformation between gamma 1, gamma naught, and gamma 1. So we have a whole sequence of geodesics gamma S, where S would be a label on each one of those geodesics, such that gamma of S equals 0 would be equal to gamma naught, and gamma S equals 1 would be equal to gamma 1. So this is S equals 0, this would be S equal 0.1, this would be S equals 0.7, and this would be S equals 1. So we have a whole bunch of geodesics, a complete family of geodesics between gamma naught and gamma 1. S is a parameter that labels each geodesic. So that's one parameter. I also need a parameter that's going to be running along each geodesic. So I'll introduce T for that. So T is a parameter that runs along each one of those geodesics. So it's the running parameter on each geodesic. So we're going to take T to be the running parameter on each gamma S, and I'm going to be assuming here that T is an affine parameter so that we have the geodesic equation in its usual form. So all of those curves will have some mathematical description in whatever coordinate system I'm playing with here. So there's going to be a description where, if you specify S and if you specify T, I know, first of all, by specifying S, I know on which geodesic I am, and by specifying T, I know where along each geodesic I happen to be, right? So there's going to be a mathematical equation that says that, for each value of S and T, I know what the position of my point is on the geodesic. By selecting S, I select one of those geodesics, and by selecting T, I happen to be here or there. So I know where I am on the given geodesic. So that would be a parametric description of the whole network of curves, gamma S. So this is selecting the curve, or selecting the geodesic, and this is selecting the point on the selected geodesic. I don't care what those functions are. I'm just assuming that, in whatever coordinate system I work with, those curves exist. They can be written in that form. Okay. That's the basic setup, and now we're just going to milk this out and see what we can get out of this. So, having the network of curves, I know that along each curve, I'm going to have a tangent vector to each curve. Either this one over here, I'll call this U, or that one over here, I'll call this also U, or the one that would be defined on the original curve, I also call it U. So U is the tangent vector field everywhere in this network of curves. So U alpha is the tangent vector field, and I can get that by basically taking those parametric equations, keeping S fixed, because keeping S fixed means that I'm moving along one of the geodesics, and varying T. So the way to calculate the vector field from the parametric description of the curve is simply to take a partial derivative of those equations with respect to t, keeping s fixed. So I might indicate this by putting that around a bracket like this, as we would in thermodynamics. You specify which variable you keep fixed. And because we keep s fixed, as we change the coordinates, we're moving along one very specific direction, this is the direction of the geodesic. And by moving in that direction, of course, that's how we define the tangent vector field. So that is the tangent vector field to each geodesic gamma s. And the claim is that, well, we're talking about geodesics here. Each curve is a geodesic, and that will satisfy the geodesic equation in a fine parameter form. So that's one thing. All right. So now I can introduce the deviation vector. Because another thing you can do with those equations is to, instead of keeping s fixed and varying t, you can do it the other way around. You can say, let me see what happens when I consider t to be fixed, and I start moving along the sequence by varying s. So I'll draw a different diagram to represent this. So we still have gamma naught, we still have gamma 1, we still have all the curves in between, but I won't draw them for the time being. But if we start moving at fixed t along s, what happens is that, well, we take a cut. What happens by doing that is that we take a cut across the geodesics like this. We move along the sequence in such a way that t is equal to exactly the same value as I cut across all the curves like this. So that's what happens when you play it the other way. You keep t fixed, you go along s, you define a bunch of curves like this that have the property of meeting each geodesic at the same value of t. And those curves are going to be important for what I want to do next. So here's one of those curves. And they have the property that, well, this is everywhere t equals 1, everywhere t equals 2, everywhere t equals 3. And what changes as you move along the curve, of course, is s. So by keeping t fixed and varying s in the relations that we were given, we define a family of cross curves, and I don't think I'll introduce a symbol for them. Those are the curves I'm talking about that that run from gamma naught to gamma 1. Yep.
How do you select where the proper time begins for each geodesic? T equals 0.
Yeah, you have the latitude to do that. So depending on how you choose to do that, as you set up the sequence here, so each value of t, so basically you can slide t up and down, up and down, up and down on any on any geodesic independently. And depending on which choice you make, you'll end up with curves that look differently over here, right? So basically, you just do it one way, you get those curves. You do it another way, you get slightly different curves, and that's fine. You just, you just do it for whatever choice.
And also, what if you have a stationary geodesic?
Stationary in the sense
that it doesn't change over. It goes. I guess never mind. But time's also a coordinate.
Right. So it would always move in time if we're talking about time like geodesics. So the problem would be if you had a geodesic that suddenly decided to stop, a geodesic with an endpoint, and well, that can happen in pathological spacetimes if you have singularities and things like that. But we'll assume here that there's no reason for it to stop. It just keeps on going. So let's keep life simple. But this issue of sliding t up and down, the origin of t up and down on each curve is something that we'll come back to. That's something that we can use actually to our advantage to impose some additional conditions. So we'll come back to that. Any other questions?
And
Yeah.
the geodesics cross each other?
Okay, so that can happen. So certainly it could be that as you set up this system of geodesics over here, that some crossings occur. Those are called caustics, and we'll talk about them when we talk about congruences. Here I'm saying that, well, we assume that this doesn't happen. And we're working locally so that, there's a possibility that this may occur at later times, but we just, we just work in a region where this is not happening. But yeah, as a matter of fact, it certainly can happen that geodesics will start crossing each other, and we saw that on the surface of the sphere, right? You have geodesics that merge at the North Pole, and that certainly can happen. Okay, so we have a family of cross curves like this, and those curves don't have to be geodesic, so I call them curves because there's really no reason to expect that they will be geodesic curves. But one thing I can do on those curves is to, again, define a tangent vector. So whenever I'm given curves, you can always get the tangent vector out of this by the procedure I describe over here. So along each curve, I can construct a tangent vector that I'll call xi. So the tangent vector to all the cross curves is a vector field that I'm introducing. And that I call xi, as I said. And this one, of course, I get by taking the partial derivatives of my relations with respect to s instead of t. And I'm keeping t fixed. So that's the definition of the tangent vector field to all those cross curves. This was the definition of the tangent vector field to the original geodesics. That is going to be my notion of a deviation vector between the two geodesics. If I take that tangent vector field and I look at the ones that are defined up here on gamma naught, what I have is something that that is close as I can make it in a curve spacetime as having this interpretation of being a deviation vector from one curve to the other one. So the notion that we could have a vector pointing from this point to that point is just not available. So that doesn't exist in differential geometry. The best thing I can do is to define a deviation vector as being tangent to a curve that cuts across my two geodesics. And what I've done here is to introduce a network of such curves. And the tangent vector to those curves is the best thing I can come up with that will have an interpretation of a deviation vector. But it's really understood in that context of being, in that sense of being a tangent vector that is tangent to those cross curves. And my deviation vector is going to be the one that's going to be defined right here on the reference geodesic gamma naught. That is, that is the setup. And once we have the setup and we agree that we're talking about this and we agree that the deviation vector is going to be defined this way, then everything else follows. Everything else is just a matter of computation. The important aspects are already captured here. We have everything we need to get going, and we have good, meaningful definitions for what we are dealing with. Any questions before I move on? So that's the setup. We have two vector fields, and they're both defined in terms of curves. And we have two networks of curves that are linked to each other. We have the original geodesics, and then we have those extra cross curves that come for free once we have the original network of geodesics. Okay. One property that comes out of the construction is that xi and u are Lie differentiated along each other. So let's see how that comes about. Suppose that I take the derivative of u in the direction of xi. What do I mean by that? Well, what I really mean by that is that I take a partial derivative of u with respect to s. Because moving along c is moving along the sequence, which means that when I do this derivative, I keep t fixed, and I just move along s. Right? So that's the partial derivative that I'm computing. And because u is defined as that partial derivative over there, we're talking about the second derivative of my relations, first with respect to t, then with respect to s. So now let's do it in the other way. Let's take the derivative of xi in the direction of u. Well, now taking a derivative along u means that I'm moving along t, keeping s fixed. So I'm taking this partial derivative. And that then becomes the second partial derivative, first with respect to s, then with respect to t. Those two things are equal. They have to be, right, for smooth differentiable functions, which I'm assuming here. Therefore, we have equality between this and that, and therefore, we have the statement that the Lie derivative of xi, which would be xi alpha differentiated with respect to u minus u alpha differentiated with respect to xi, vanishes. So, bottom line is that we have that the Lie derivative of xi with respect to u is 0. That's the same thing as the xi derivative minus, xi derivative of u with respect to xi. That's equal to 0. And the useful way to express this is to say that the covariant derivative of xi in the direction of u is the same thing as the covariant derivative of u in the direction of xi. That property comes for free just as a benefit of the construction. So it just comes about just from the construction. That will give us all sorts of other goodies, and that also is going to be the key to coming up with the equation of geodesic deviation. So no mysteries here? It's all good? Okay, let me just combine these things and show that the inner product between xi and u is a constant everywhere. So that comes out. So I want to calculate that that this inner product between the two vectors is actually a constant as I move up along the congruence. So I have the derivative of a scalar, which I can re-express as I did before this morning as a covariant derivative of a scalar along the congruence. And what that means is that I take xi, I differentiate with respect to u, and so here I'm applying the chain rule, and I leave xi alone, and then I differentiate u in the direction of u. Right? So at this point, this is the same calculation that we did for proving that when you have a killing vector, this is a constant of the motion, but here we don't have a killing vector. So I'm using the same notation, but xi is not a killing vector. It's a deviation vector in this case. All right. This is 0 by virtue of the geodesic equation, so we have that. This can be re-expressed as the other derivative. So I'm going to make the switch here, where this can be expressed in this form right here. Here I have u alpha differentiated in the direction of xi that multiplies u alpha. That turns out to be the same thing as u alpha differentiated in the direction of xi. Right? Because, and there's a factor of 1/2, because when you expand this out and apply the product rule again, First, you're going to be differentiating this with respect to beta in the direction of xi. This is being left alone, so you get this back. But then you're going to leave this one alone, differentiate this in the direction of beta, and multiply by xi, and you get again this with indices, switched around. But basically, you get twice the same thing. So this is the same thing as that, and that's a trick I'll often use when you see something differentiated that gets multiplied on the right-hand side like this. Well, you know that you're actually, differentiating in the square. So, differentiate x squared, you get, twice x times the derivative of x. That's what we're seeing here. But that is 0 because this, we know, is a constant. If t was proper time, then this would be normalized to -1. So that's a constant everywhere along the congruence, everywhere, in my network of curves. So u would always be a constant, and it's going to be the same constant as I go, from one curve to the other curve. So as I move along c, I get exactly the same normalization constant. And therefore, the right-hand side is 0. And therefore, this is a constant everywhere in that network of curves. Again, all of this comes for free as a result of the geometrical setup that we started with. Now, what can I do with this? One thing I can do is to actually make this equal to 0. I can prove it formally. I think I'll do that. But it's back to your issue of sliding the origin of the parameter t. When I was setting up my parameterization in terms of the affine parameter t, as we said before, so I know the rate at which t has to change because it has to be an affine parameter as it goes along the curve. But I have a lot of latitude in saying that if t is equal to 0 here, where am I going to set t equal to 0 on the next guy? Where is it going to be on the following guy? Where is it going to be on this guy? And so on and so forth. So the origin of t on each word line, on each geodesic, is something I can adjust. And if you think in terms of the diagram over here, if you were to pick a sequence where t is equal to 0 here, and here, and here, and here, and here, the curve you would be constructing would go like this, the deviation vector would go like this, and those two vectors would not be orthogonal to each other, the u and the xi. Right? But if you adjust the origin of t correctly, if you do it right, and you say that t is going to be equal to 0 here, and then here, and then here, and then here, and then here, then the curve you're going to be constructing is going to be orthogonal to the first, to the geodesic. And that deviation vector evaluated here is going to be orthogonal to u. So the point is that you can adjust the origin of the parameter along each curve to guarantee that u is going to be orthogonal to xi when you evaluate it right here. And if you do that here, then of course the construction guarantees, because of all the Lie derivative conditions that we derived, guarantees that this orthogonality condition is going to be true everywhere. You got a question?
So is this constant? It's constant along but it's not necessarily constant along the cross curves. We have to set the initial conditions on each cross curve such that it can also be the same.
That's right.
Okay.
That's right. Yeah. So you're right. So this measures what happens to that quantity as I move up along one of the curves, and there's no guarantee that as I move across curves that you would preserve the same constant. So what I'm going to do, the only place, so what I want to do here is to set it up in such a way that it's going to be 0. The inner product is going to be 0 right here along this curve, and then it's going to be true. It's going to be true everywhere along the curve. Okay. So I think you can see that, graphically you can make this happen by just sliding the origin of t in the right thing. In the right way. There's also a very quick, little formal proof that you can go through that will convince you that you have the freedom of choosing the constant here to be 0 along one of the curves, including gamma naught. So I think I'll just go through that just to see how it works. It's one of those things that you often have to do when you go through a calculation like this. So we have a vector xi, and we still have some latitude in choosing its direction, right? So that vector will have a component along u, and it will have components orthogonal to u. So I can do a decomposition like that. So xi can be decomposed as one component along u, I'll call it lambda, plus orthogonal components, and I'll call those xi tilde. So what I'm saying here is that I'm writing xi in terms of a component along u, so lambda would be defined as minus the inner product of xi with u, and xi tilde is restricted such that its inner product with u is going to be 0. So that's the decomposition. So this is by definition orthogonal to u, this is along u, and the component along u is lambda, and by the theorem over here, we know that lambda is actually a constant. Right? So what I'm going to try to do here is to show that I can always kill off this component. I can always replace xi by its orthogonal piece and not change anything to what I've talked about before. In other words, I can always arrange things such that lambda can be chosen to be equal to 0, and that's back to my, to my discussion of before. Okay. So the claim is that in everything we've done, we can replace C alpha by its orthogonal piece without changing, without breaking anything. So if I claim that I can do that, then I have to show that xi tilde is also Lie differentiated along u, that all those properties are preserved, right? So, so let me just prove this. So we need that, and let's see, do we need anything else? No, that's pretty much it, because that's really the most important property. We have the Lie derivative property that gave us this, and now I'm arguing that we have the additional freedom of killing off this component, but it has to be true that if we do that, we don't break anything that we've derived before. So let's see. Let's see what happens. So xi alpha tilde can be differentiated along u. So what does it mean? So it means that I go back to xi. I subtract the piece that goes along u. And I calculate this, and then I get the first term, which was the same as what we had previously. And then there's nothing else, because lambda is a constant. I don't need to differentiate it. And then when I differentiate this, I get 0 from the geodesic equation. So that's all we get. So that's looking good. Now the other piece. Well, it's the same thing, right? Because here we have, it's u beta, it's xi beta. So we get this guy over here. And over here, I get xi beta minus lambda u beta. And again, I get the first piece back. And I get nothing more because, again, the extra term will be 0 by the geodesic equation. So this minus that is equal to this minus that, which is 0, which is the statement that we have, by basically removing this piece from the original deviation vector, we haven't changed anything that we had derived before. So basically, we can proceed with C tilde instead of C, and just assume that the vector is going to be orthogonal to U on gamma naught, and that's what I'm going to be doing. Or we can recognize that we have the freedom to set lambda is equal to 0, that is, to use this property and adjust the parameterization in such a way that, that the constant is actually equal to 0, so that, in fact, there's no difference between C and its orthogonal piece. So I'll just proceed and just forget about the distinction between C and C tilde. I'll just work with tilde under the assumption that, that we have this condition right here. So now we're going to impose that U alpha is orthogonal to C on gamma naught. So that's a condition that I'm imposing everywhere on gamma naught, but I don't care outside of that. All right?
So basically, you're saying that you have freedom in the definition of time, constant t curves. So your constant t curves here is the integral curves of this integral.
Yep. Right. But I start with the curves. So I start with the curves, and it's just that which curves I'm going to draw will depend on what I assume to be the relationship between t equals 0 on this curve and t equals 0 on that curve, and so on. So under this, this freedom that I have of sliding up and down t, I'm going to draw different curves, and I here choose to adjust the parameterization so that this curve and all those curves are going to be orthogonal to gamma naught, at gamma naught. So that's all I'm doing. Okay. Well, now we have everything we need. Now it's just a matter of doing, a calculation involving a few lines, and then we're going to have our equation for geodesic deviation. So it takes a little bit of time to set it all up, but I think I like these kinds of setups. I like to take my time to set it up right, so that after that you know exactly what you're doing, and you can see your way through the calculation very clearly. So let's just proceed. So what I want to calculate here is well, we have to think about that a little bit. So if I'm in flat space and I start with parallel geodesics, that is parallel straight lines, I find that the deviation between the two is always going to be a constant. So that deviation vector will have no time derivative and certainly no acceleration. So when you start geodesics parallel in flat space time, you have a constant deviation vector between the two that has no that has no velocity and no acceleration. Right? Nothing changes. If I don't start the geodesics parallel, if I sit and I'm going to take this straight line and that straight line, here's a situation where the deviation vector actually increases, right? The separation between the two geodesics increases. But because I'm talking about straight lines, the velocity, the relative velocity of this guy relative to this guy is going to be constant. It's a linear increase in the relative distance. And that means that the velocity is going to be a constant, and that will have zero acceleration. So in general, so as long as you're talking about flat space and straight lines, the diagnostic that you're dealing with geodesics that are straight lines in a flat space is that there's no relative acceleration between your geodesics. So what I want to calculate here is an acceleration vector for the deviation vector. And the claim is that this being non-zero is going to be a diagnostic for curvature. Because if you didn't have curvature, if you were in flat space, you would be dealing with straight lines, and the deviation vector would have a zero acceleration. That's the thinking. So the starting point is just to say that we're going to be calculating the covariant acceleration associated with the deviation vector. So the first time derivative would be the relative velocity. The second time derivative is the relative acceleration. And it's the relative acceleration of course, gamma 1 relative to gamma naught. Okay, what do I mean by this? Well, first I take the first covariant derivative, and that would be this operation. And now I calculate this derivative, which is the second derivative operation. Okay, now I have to follow my notes because there's lots of ways you can get lost in this calculation over there. And I wouldn't want to do that. All right. First thing I'm going to do is to change this by the other combination that comes from the Lie derivative condition. So I know that this is also equal to that. So that comes from the Lie derivative condition, and that's going to be my first step in the calculation. Now I'm going to expand this. I'm going to expand the covariant derivative. So I have two covariant derivatives on my velocity field, u. I multiplied by u beta. I multiplied by, sorry, that's a gamma. So I'll multiply by c beta u gamma. And then I have the next term, which is u alpha comma beta, semicolon beta, c beta, semicolon gamma u gamma. All right. What I'm going to do next is to play a trick. I'm going to take this and I'm going to change the ordering of the two indices. And I can do that if I introduce a Riemann tensor. And the reason why I'm doing this is that, well, basically anything but the term involving the Riemann tensor will eventually disappear from the calculation. So I'm bringing out already the outcome by doing this little trick. So the first term I'm going to write as u differentiated first with respect to gamma, then beta. And I never remember the placement of indices. So this I can do at the price of introducing a Riemann tensor. And the indices are alpha mu, beta, gamma, u mu. So all of this stands for this. We get c u gamma. And then for the second term, I'm going to play that switch trick again. I'm going to replace the derivative of c along u by the derivative of u along c. Right? So let me bring out the Riemann tensor term first. And then I have a couple of leftover terms. I have the u differentiated twice. And then I have the other u. All right. What do we do next? I haven't involved the geodesic equation yet, so I'm going to put it in. What I'm going to do is to rewrite this by essentially factorizing the beta derivative. So I'm going to rewrite this as u alpha semicolon gamma u gamma, all differentiated with respect to beta and then multiplying by C beta. But now I have to compensate. So if I apply the product rule on this, I have, the first thing I differentiate is this guy, then I have U gamma C beta, so I reproduce this. But then I have the extra term, so I have to remove this. And the extra term is where I have this left alone and this differentiated. The point of doing that is that, of course, this is 0 by virtue of the geodesic equation. And now what do we have? We have exactly the same term, but with a minus sign, so they cancel out each other. So here, the placement of the indices is a little bit different. Here I have beta as the first dummy index, and here I have gamma as the second dummy index. Here I have gamma as the first dummy index and beta as the second dummy index. But you know that we can always relabel those dummy indices so that, in fact, this is exactly the same as this, and all the mess that's left over after the Riemann term actually cancels out. But in order to make it cancel out, I had to involve the geodesic equation so that we got rid of that as well. So what's the bottom line? The bottom line is that the relative acceleration of my deviation vector is directly proportional to the Riemann tensor. And therefore, I have a one-to-one correspondence between the non-zero relative acceleration, as we discussed previously, and the presence of curvature as measured by the Riemann tensor. So if the Riemann tensor happens to vanish, then there's no relative acceleration, and the geodesics will be straight lines, and those straight lines will not, the straight lines can still go like this, but there's going to be a non-zero acceleration for the deviation between the two. So if this is 0, this is 0, but you can put it the other way. If you say that, well, if you observe that your geodesics in your space-time have a 0 relative acceleration between each other, then that guarantees that the right-hand side is 0, and that guarantees that the Riemann tensor is 0, and therefore that it's a flat space-time. So the best way of thinking about curvature is really contained here in that equation. And the key is to think about how geodesics behave relative to other geodesics. If you find that they tend to converge or diverge from one another at an expanding or at a rate that changes, if there's a non-zero relative acceleration between geodesics, you know that you're dealing with a curved space. If not, not, right? So one way to think about this, is to think about very simple examples. So we talked about the surface of the sphere, and we recognized that we had geodesics converging toward the North Pole, and it's that convergence property that tells us that we have a non-zero relative acceleration between geodesics. And in fact, it's a shrinking distance, so we have a convergence properties of those geodesics, and that convergence property, that nonlinear convergence, is something that tells us that the surface of the sphere is actually curved. Now, that surprises no one, but an example that sometimes surprises somebody is if instead of a sphere, we talk about the surface of a cylinder. If I take a sheet of paper and I wrap it up like this and I form a cylinder, to me it looks curved. And it requires a little bit of training to recognize that intrinsically this is not a curved surface. And one way to think about this is to think that, well, if you think of geodesics on that surface, well, they're all going to be circles wrapping around the cylinder. But those geodesics are, two geodesics like that, right? And they're not diverging, not converging away from one another. They stay perfectly parallel at all times. And that's a diagnostic that there cannot be any intrinsic curvature on the surface of a cylinder. And that's not surprising because, well, all I've done is to do a periodic identification of points on the sheet. So those geodesics before the wrapping were perfectly straight, perfectly aligned. There was never any curvature, and the wrapping up doesn't produce any intrinsic curvature. It's obvious after the fact, but one way of thinking about this is to recognize that curvature has to be associated with either a diverging property of geodesics or a converging property. And if you don't have any of that, then you must be dealing with a flat space.
That's only for geodesics that start parallel.
No, so even if I didn't start parallel, so if I start with one straight line like this, another one that goes up like that, after I'm wrapping up, so the point is that they are diverging away from another. So you would have this one over here. I'm not sure if I can illustrate that, and that one over here, right? So they are moving away from one another, but they're doing it linearly. So it's the nonlinear diverging or converging that is key here. You really need the non-zero relative acceleration. You can have a non-zero relative velocity, that's fine, but it's the acceleration that measures the curvature. Later on in the course, we're going to be distinguishing, in a situation like this with the cylinder, we're going to be distinguishing what is intrinsic curvature versus the recognizable fact that we do have some curvature somewhere here, but that's the extrinsic curvature. We have a bended surface in an external space, in a three-dimensional external space. So when we deal with hypersurfaces, we're going to be introducing notions of intrinsic curvature and extrinsic curvature that distinguish what is purely intrinsic to the surface and what is a property of the way it's embedded, in a enveloping space. You have a question?
Where do we use the orthogonality of U and C in that derivation there?
We didn't. So in fact, it's not required. It's not necessary. But I think it's still something you would want to have just to firm up the interpretation of C as a deviation vector. So if I wanted to draw a deviation vector between two geodesics, probably I would choose the one that's actually orthogonal to the first. So it's just something more that you would want to impose just to have the interpretation pinned down. But you're right. I mean, it really plays no role in that proof. Any questions about that? So this type of construction we'll encounter again when we talk about congruences of geodesics. So here we got started with only two geodesics and decided that in order to make the notion of a deviation vector meaningful, we had to introduce a whole family of interpolating geodesics in between. So when we talk about congruences, we're going to be given a whole family of geodesics to begin with. So it's going to be all given to us, but we're going to be playing very similar tricks and doing very similar things. And again, we're going to be describing the behavior of one neighboring geodesic relative to a given reference geodesic, and we're going to have a deviation vector, and we're going to go in a little bit more detail into how it actually behaves as you follow the motion of each of the reference geodesic. So that is something that will come back to us when we talk about congruences. And I think I'll be ready to do that, starting next week. I want to do one more thing before I wrap up chapter 1, and I think I have just about enough time to do it in the next 20 minutes or so. One thing I haven't talked about is this notion of local flatness. And that's something that's pretty important in geometry, and it's also pretty important in gravitational physics. So a manifold can be as curved as you want it to be, but there's still this notion that if you look at a very small patch, it will look locally flat, right? We certainly know that from a long experience on the surface of the Earth. There was a time where we didn't know that the Earth was a sphere. There were people in the past who weren't crazy, but still thought that the Earth was flat. And that's because, having experience over a very small neighborhood, your city, your country, you may not recognize that there's curvature there, and that's just a statement that locally any curved manifold can be described as being almost flat on a small enough patch. Geometrically, I think that sort of makes intuitive sense. We see that from the surface of the sphere, for example. In gravity, what that means is that at any local place in space-time, you can always pretend that very locally in your immediate vicinity, space-time is actually flat. And the place where it plays the most important role, the most meaningful way of stating this is, in fact, the statement that if you're freely falling in space-time, then on your word line, in your immediate vicinity of your word line, space-time is locally flat. So I just want to flesh this out a little bit and show how this is proved, how we actually describe this mathematically. When we're dealing with a Riemannian manifold. So that's the topic of local flatness. So I've been talking about, local patches, local immediate neighborhoods. The technical way of stating this is to say that for any Riemannian manifolds, even pseudo-Riemannian if we do space-time, there are coordinate systems. There exists a coordinate system such that at any point P, but only there, at any point P in space-time, you can find coordinates in such a way that the metric at P is given by the Minkowski metric, and such that, there are two ways of saying this, such that the partial derivative of the metric at P is equal to 0. Or another way of saying this is to say that the Christoffel symbols at P happen to vanish. What you can never guarantee, unless you're dealing with flat space, is for second derivatives of the metric to also vanish. So if you think of expanding the metric in a Taylor series in that coordinate system, the first member in the Taylor series is going to be the Minkowski metric. There's going to be no linear term in the Taylor expansion, but in general there will be second order terms, and then third order, and then fourth order. If the curvature vanishes, then you can arrange for the second derivatives to vanish and all the other ones too, and you're back in flat space-time using Cartesian coordinates. Yep.
That mathematical statement, is it for any point P there exists a coordinate system that has those properties?
Yep.
Okay. So not that there exists a coordinate system such that every P has those properties.
It only holds at one P. Right? So you can do an independent construction here at P, another one over there at Q, but what you cannot arrange, of course, is for the metric to be everywhere equal to the Minkowski metric in between, right? So it only holds at one point, but it doesn't matter which point so it's really any point P, but the statements refer to one very specific point. Okay. Now in the book, I actually go through a proof of this, and it's a rather dumb thing. I mean, it's really not illuminating in the least. So the way to prove this is that I actually count the number of functional degrees of freedom you need to have in order to find a coordinate transformation that will enforce those properties. And the bottom line is that you can always prove that you can enforce this, and then you have remaining coordinate freedom left over, because this tells you that the local frame has to be Minkowski, but it doesn't give you an orientation for the axes. So you have the ability to perform boosts and rotations, and you can still enforce that. When you continue the counting, you find that you have just enough, functional degrees of freedom to actually kill the first derivatives of the metric, and then you run out of freedom, so you cannot do that on top. Well, you can do that, and you can show the existence, but it tells you nothing about the nature of that coordinate system. And that's unfortunate, and I have to say mea culpa there. I mean, I wrote that section just doing that, but I felt bad after the fact, because even though I have a proof, I have no insight as to what those coordinates may mean, how you might construct them, and so on and so forth. And it turns out that the construction is so simple and it's so pretty that I have to tell you about it. So I'm going to tell you about it right now. There are lots of ways you can do that, but there's one particular meaningful way of doing it that is really, I think, the way to go in those types of situations, and that's called the Riemann normal coordinates. Well, again, I'll present it as an existence statement first. So there exist coordinates x alpha such that around P, that point that we were talking about before, the metric can be expressed as follows. And that's a little bit more informative version of the statement I had on this blackboard. Clearly, what we have here is a particular realization of the local flatness theorem, because it's pretty clear that if, so around P, I should have said that at which x alpha is equal to 0, so P is the origin of that coordinate system. So if x is set equal to 0, if I'm at P, then G is going to be equal to the Minkowski metric. So I have the first statement. If I calculate partial derivatives of G, this term over here that involves the Riemann tensor starts at quadratic order. When I take a first derivative, it ends up being linear in x. When I set x equal to 0 so that I'm at P, those partial derivatives vanish, right? So this coordinate system and this form for the metric imply this. And it also implies the rest of it, because if I now take two partial derivatives, the term quadratic in x will become x independent. And that tells me that the second derivatives of the metric in that coordinate system end up being related to the Riemann tensor. And if the Riemann tensor is not 0, then I cannot arrange for the second derivatives of the metric to be 0. I should tell you that those are the components of Riemann at P. So in this expression, the Riemann tensor is actually a constant. It's the Riemann tensor evaluated at P. I'm killing off the cubic terms and higher order terms, but you can write down this expansion for the metric to a very large, to a very high order. At order x cubed, you would find that the coefficient in front of the three x's would be proportional to the gradient of the Riemann tensor, the covariant derivative of the Riemann tensor evaluated at P. At order x to the fourth, it would get complicated. You would have two derivatives of the Riemann tensor, but you also have Riemann squared terms, and the number of terms that you would have to include to make it all work out would increase. At order x to the 5, well, now it becomes a real mess, because you have, well, on top of, well, no, actually, at that order, you would have only three derivatives of the Riemann tensor, and then you would have terms like grad Riemann multiplying grad squared Riemann. I mean, it would get messy. And beyond that, you would get Riemann cubed. You would get all sorts of things. But anyway, when you truncate it to second order, it actually looks pretty simple. So this is an example of a metric you can work with that incorporates, that sort of enforces local flatness. It's an example of one of those coordinate systems that have this property where the metric is equal to Minkowski at P, and the first derivatives, and therefore the Christoffel symbols, happen to vanish at P. And it's an explicit metric. These guys are a bunch of constants, so it's a metric that's explicitly quadratic in the coordinates. And you can do all sorts of calculations using this metric, and sometimes, very often, actually, it turns out to be very handy to do that. Okay. Well, here I didn't tell you anything about how you might set up the coordinate system. Here I haven't told you anything more about how you might set up this coordinate system. And here's where it really gets pretty. So I want to describe that. I won't prove it, but that's something you can do yourself as a little challenge. So before I do the construction for curved spacetime, I'll just remind you of how you might set up Cartesian coordinates in flat spacetime. I mean, you'll tell me you know how to do that, and I'll say sure, but maybe you haven't thought about it just the way that I want to think about it right now. And after we go through this little story, you're going to know exactly what needs to be done in curved space-time. And the claim is that that's how you construct this coordinate system over here. So let's do flat space. And here I don't care whether I'm talking about 3D space or what. Let's do something in flat space. OK. The first thing I need to do in flat space to start constructing a coordinate system is to select an origin. So we're going to select a point P. That's my P. First thing you do. The second thing you do is to say, well, I'm going to need a frame. I'm going to need to pick 3 directions that are going to be my reference directions. Right? So you construct a frame. And a frame in our context here is just a set of 3 or 4 basis vectors, unit vectors that point in the 4 independent directions. Here I'm going to draw 2. So here's E1, here's E2. So once you have an origin and once you have a frame, well, you pretty much have everything you need. OK. I want to construct the coordinates, the Cartesian coordinates of another point, say Q. So here's Q. So I want to construct the coordinates of Q. The recipe is to say I'm going to draw a straight line between P and Q. Here's the straight line between P and Q. And I'm going to measure how far going along that straight line Q is relative to P. And that's going to be my radial distance. Having drawn that space, that straight line between P and Q, the last thing I need to do is to draw the unit vector that points in that direction. That unit vector lives right here at P. Okay? So in order to define the coordinates, now I need to complete the story, and I say that the first thing I'm going to do is to decompose n into the basis that's given to us. So n as a vector is going to be decomposed in terms of components in the frame that we selected. And of course, the value of those coefficients over here will depend on which directions I pick to be my reference directions. So that's the decomposition of n in the frame. We're gonna write down the position vector of Q as, I'll call it x, and x is going to be r times that unit vector, because I know that r is the distance between P and Q. And that then can be written as r and j that multiplies the basis vectors. And the bottom line, the last step, is to say we're going to assign to Q the coordinates, which happen to be Cartesian coordinates, xj equals nj times r. That's the construction. And I don't think there's anything surprising here, except that perhaps you haven't thought about doing it this way, this very particular way, before. Having assigned those coordinates, you can then verify that the metric in that coordinate system for that space is going to be the usual, Kronecker delta metric, the flat Euclidean metric. I mean, that's a very trivial step that you can do on top of that. An outcome of this construction is that the metric is delta ij, if we're dealing with 3D space. If I were doing this in 4 dimensions, of course, we would get the usual Minkowski metric. In curve space, we don't need to change one thing. Well, we need to change one thing. We only need to change one thing, and the whole construction carries over without any further changes. What's the one thing? Yeah?
We'd have to replace the straight line by geodesic.
Exactly. Sort of suggests itself, right? I mean, I was using a straight line in Minkowski space, in flat space, because that was, preferred because it's a geodesic of that space. While if I'm dealing with a curved space, presumably I can repeat all of this and use a geodesic instead of a straight line. I mean, that's the next best thing, right? I wouldn't have a straight line to use anyway, so I have to use a geodesic. But the claim is that I can carry over exactly the same construction with a geodesic instead of a straight line, and everything else goes through. So let's think about this. What do I do in curved space? Well, again, I pick my origin, and I can do that wherever I want. Again, at that point, I can select a tetrad, 4 basis vectors that will point in the independent directions in my space-time at that point. So I erect, a set of basis vectors at that point. So here's E1, E2, E3. So that I can do just as well on a curved manifold as I can in flat space-time. Next, I look at Q. And now the only step that's different is that the line I'm going to draw between P and Q is not going to be a straight line. It's going to be the geodesic that links those 2 points. There's an essential assumption here is that the geodesic has to be unique. And that turned out to be true only if Q is sufficiently close to P. If you go too far away, then the geodesics can be non-unique. So you can have more than one geodesic linking the same 2 points. And you can think of this on the surface of a sphere, right? On the surface of a sphere, you talk about the great circle. So think of the equator. If we have 2 close points on the equator, the geodesic between them is unique. If you take the 2 points to be on opposite side of the sphere, then you have one, you have a half great circle on one side, the other half great circle on the other side. So you have 2 geodesics relating to, linking the same 2 points. So we need a unique geodesic between P and Q, and that means that we can do this in a local neighborhood. We can't do that arbitrarily far away. Well, the rest goes through because, I can measure proper distance along that geodesic. I call it S. I have a normal vector, a tangent vector to that geodesic. I can call it U instead of M, but it's exactly the same thing. So I have the tangent vector to the geodesic. It lives at P, so it can be decomposed into the basis that I have here. So we're going to decompose U alpha as, I'll write it as, you won't like it. Maybe I'll put a bracket here, maybe a bracket there to distinguish the space-time index alpha from the label that I pick, so that I use when I pick my basis vectors. Right, so this is a label on the basis vectors, and this is the decomposition of U in that basis. I can still do that. That's analogous to that point over here. I don't have a notion of position vector, so that changes. That doesn't exist anymore. But that's fine. I don't need it. In fact, I can bypass that step entirely. I can go from this directly to here by declaring that my coordinates, the Riemann normal coordinates, are going to be defined to be x mu, and they're going to be s that multiply those coefficients in the decomposition of U in the selected basis. The claim is that if you define the coordinates in this way and calculate the metric in that coordinate system, you'll end up with that expression right here. When you look at this, it's pretty remarkable because I think the construction is really simple, right? But when you look at the mathematical representation of, so this is the coordinate of this is the the coordinates of Q relative to P in Riemann normal coordinates. But this equation basically refers to this tangent vector. So as you keep pushing S beyond Q, you basically follow the geodesic beyond Q, right? And you can go as far along the geodesic as you want. So this equation is not only an equation that describes the coordinates of Q, it's also an equation that describes the entire geodesic that passes through Q if you use S as a running parameter on that curve. If you were to draw the geodesic in whatever curve space-time you're given, it might look very weird, it might look very bent, and so on and so forth. Mathematically, in Riemann normal coordinates, this is an equation of a straight line because this is a constant coefficient that multiplies the distance along the curve, and that's the description, that's the mathematical description of a straight curve. So Riemann normal coordinates have the property that geodesics in those coordinates look straight mathematically. They don't look straight when you visualize them in the actual manifold, right? The curves in the actual manifold will be bent like the manifold is. But the mathematical representation, when you stare at it, looks like the description of a straight line. That's the meaning of the Riemann normal coordinates, and that's the construction that gives you this metric right here. Okay, I'm going to say one more thing, and then I'm going to quit. There's a variation on that theme that turns out to be extremely powerful and makes a very deep statement about relativity, about physics in a gravitational field. Instead of focusing at a given point, what I can do is to focus on an entire geodesic. So suppose I have a time-like geodesic. I can do a construction like this where instead of shooting off geodesics in all possible directions, I shoot off geodesics orthogonal to my word line. That's the notion of Fermi normal coordinates that I'm talking about here. So there's a variation of this known as Fermi normal coordinates. Where instead of focusing at one event in space-time, we take an entire geodesic as the origin of our coordinate system. So we take a time-like geodesic as the origin. So here's our here's our time-like geodesic. I might as well call it gamma. I always call it gamma. Gamma, there's going to be a proper time parameter on gamma that I'll call t. And gamma is going to be the place where the spatial coordinates xj are equal to 0. And to find the spatial coordinates of a point q, what I'm going to do is to draw a geodesic from q to gamma. And that geodesic is going to have the property that when it crosses gamma, it does that at right angles. It's orthogonal to gamma. But other than that, it's going to be exactly the same construction. So to Q, I'm going to assign the same time coordinate that I had up here. And the spatial coordinates are going to be constructed in exactly the same way. I'm going to take this tangent vector. I'm going to decompose it in a triad of vectors that I'm going to be defining here. And I'm going to construct coordinates in exactly the same way by using the spatial distance away from gamma as I go toward Q, as in the same way that I did before. So I can refine the construction so that now the central point of the coordinate system is going to be an entire time-like geodesic. It's important that it's a time-like geodesic for what I'm going to be saying next, because what I want to tell you next is that the metric in that coordinate system is just extremely pretty. GTT is -1, and then there's a Riemann tensor term. And then we have something quadratic in the spatial coordinates. The spatial components of the metric are 0 except for a quadratic term. And then the spatial metric is Euclidean up to second order terms. So what do we have in here? Well, we have something that looks a lot like what we had before in Riemann normal coordinates. We have the metric given by Minkowski values at x equals 0, except for terms that involve the Riemann tensor at second order. And we don't have any linear terms. So that's another coordinate system that enforces local flatness. But now we have local flatness everywhere on the geodesic. We have the metric taking Minkowski values everywhere on the time-like geodesic. And we have the first derivative of the metric being 0 everywhere on the time-like geodesic. As I go away from the geodesic, we deviate from the Minkowski values by terms of quadratic order. Those coefficients involve the Riemann tensor. Before, the Riemann tensor was a constant because it was evaluated at p. But now the Riemann tensor is evaluated everywhere on that time-like geodesic, and it becomes a function of the running parameter on that geodesic. So the Riemann tensor here becomes a function of time. What does it mean? Well, it means that, in fact, the statement of local flatness is not limited to a given point. You can take it all the way. You can take it to apply along one specific geodesic. So you can select a geodesic, and you can have local flatness everywhere on the geodesic. And that's the statement that if you happen to be freely falling in space-time, if you follow yourself a time-like geodesic, none of us are, by the way. Sorry about that. You can jump on the table, and for a brief while, you'll follow a geodesic. But if you were to follow a geodesic in space-time, you could set up a coordinate system like this. You could set up Fermi-normal coordinates in your immediate neighborhood. And the statement is that, apart from those quadratic terms in the metric, you would never see the difference between, the global metric of the space-time around you and a flat metric. So that's the statement that as you're freely falling in a space-time, in your immediate neighborhood, space-time is locally flat everywhere along your curve, everywhere along your time-like geodesic. And that means that for you, gravity doesn't exist. So if you're over there falling toward Earth, gravity doesn't exist locally because you can claim local flatness anywhere around you for the duration of your time-like geodesic. If you're over there, if you're over here and then there's somebody else over there also freely falling in your space-time, that person also can claim that in my vicinity, there's no gravity. So we have two distinct observers saying that there's no gravity anywhere, but those geodesics happen to be converging toward each other as they both fall toward Earth at a nonlinear rate. It's that convergence property that convinces them that, in fact, there must be something there to explain this phenomenon. They don't see it locally anywhere, but they see this global property of geodesics to be converging toward each other at a nonlinear rate. That property is curvature. That property is tidal forces. That property is the Riemann tensor. And that is true gravity. Fake gravity you can always remove, not just locally, but everywhere. That would be the case of a uniform gravitational field. True gravity you cannot, because you can never beat the Riemann tensor. But locally you can always remove it. I mean, there's always a locally moving frame, a frame that moves with an observer on a geodesic, around which gravity might as well not exist, because you just don't see any effects of gravity unless you start probing larger distances, large enough so that those terms start to matter in the expression for the metric. So that I find very compelling. It's something that actually I have used a lot in my own research. So, when I talk about the motion of a particle in space-time, and I want to describe, either tidal effects or effects of larger bodies or things like that, if I'm only interested in what the particle is doing, I might as well work only in the vicinity of the particle, and that's a very good coordinate system to be using. And in a lot of my work that I've done, I've actually exploited Fermi coordinates or variants thereof to do my calculations. And this property that it's locally flat, except for quadratic terms, ends up being an essential part of simplifying the calculation. And you can make a lot of progress that way. So you can use this, you can use that when that is more appropriate. That's a little bit simpler to deal with. But those are very good things to use, very good coordinate system to use when you have a purely local interest in something. They're not so good to use if you are trying to probe larger regions of space-time. But if you work locally, they're just wonderful things. And sometimes you don't even need to know what the coordinates are. Sometimes all you need to simplify calculations is to rely on those properties right here. And we'll have some situations in the course where we'll use that, but now I think you know more about all of this and how it all fits together. So I think that's all I had to say today. Any questions before we disperse? Okay, so that's basically wrapping up chapter 1. So next week I'm going to get started with chapter 2. So maybe you can get ahead of myself a little bit by start looking into energy conditions. So the first section of the book is a refresher on energy conditions. Maybe you can get started looking at that. I'll cover that very quickly, but then I'll go into the rest of it in some detail. All right, I'll see you next week.